Welcome to another episode of Breaking Math, where we dive deep into the fascinating intersections of mathematics, science, and real-world problem solving. I'm your host, Autumn and with me, as always, is my illustrious co-host, Gabriel Hesch. Today, we're exploring the cutting edge of fire science, looking at how innovative technologies are changing the way we understand and investigate fire behavior. Specifically, we'll be discussing a groundbreaking research project with two scientists that work at the National Institute of Standards and Technology, or NIST, that uses photoacoustic technique to measure soot deposition on surfaces. This research holds exciting potential not only just for improving fire safety, but also revolutionizing forensic fire investigations by providing a more objective and accurate way to analyze burn patterns. To guide us through this complex and impactful topic, we're thrilled to have two distinguished experts in the field of fire research and technology that work at NIST joining us today. Our first guest is Amy Mensch, a mechanical engineer in the Engineered Fire Safety Group at NIST. Amy has spent more than a decade working at NIST's Fire Research Division, where she has tackled a variety of critical topics such as the thermal performance of firefighter equipment, soot and smoke behavior, kitchen cooktop fire prevention, and even the ignition of firebrands, also known as embers, that can spread rapidly in wildland settings. Amy is not only at the forefront of fire safety and research, but she's also a passionate advocate for women in STEM, playing active roles in affinity groups both at NIST and the Department of Commerce. She also contributes to the broader engineering community through her involvement at the American Society of Mechanical Engineers. Today, Amy will help us understand the role of soot deposition in fire dynamics and how her work is contributing to better fire safety standards. Also joining us is Ryan Falkenstein-Smith, a mechanical engineer in the firefighting technology group at NIST. Ryan has earned his PhD in mechanical and aerospace engineering from Syracuse University, where he focused on high-temperature membranes for oxy-fuel combustion, a key technology in clean energy research. His expertise in high-temperature environments has seamlessly transitioned into fire research. As a postdoctoral fellow at NIST, Ryan developed a validation data set for pool fire character, which are used to support the International Association of Fire Safety Sciences Measurement and Computation of Fire Phenomena Working Group. His current work centers on smart firefighting technologies, tools that are transforming the way firefighters respond to emergencies. These include gas extractive devices that predict backdrafts and non-invasive analytical tools that improve situational awareness in the midst of a fire. Ryan's focus on making firefighting not only safer, but smarter by integrating advanced technologies into everyday operations. Together, Ryan and Amy have collaborated on a fascinating study that uses the photoacoustic effect, a process where light, in this case from a high-intensity flash, is used to generate sound waves from soot particles deposited during a fire. By measuring the sound waves produced, they can accurately gauge the amount of soot deposited on surfaces, which is critical for both understanding fire behavior and reconstructing events post-fire. This technique offers a non-invasive way to measure soot deposition, which could prove invaluable in forensic fire investigations. By providing a more objective measurement of burn patterns and fire exposure, it allows investigators to draw more precise conclusions about how a fire started and progressed. In today's episode, we'll dive deep into the specifics of their research, explore the technical challenges they faced, and discuss the broader impacts of this work. From predicting fire hazards in real time to improving fire science investigations, this conversation will give us insight into how fundamental science and cutting-edge technology are working together to make the world a safer place. Now, before we begin this episode and before you hear our intro from Breaking Math, we're going to play a small clip that actually gives you the sound of what you hear during this technique being used. Check it out. Did you hear those popping noises? Let's jump into the rest of the episode. Hi, Amy. Hi, Ryan. How are you doing today?
Thanks for having us.
Thanks for coming on the show. Now, tell us a little bit about yourselves and what got you interested in this work.
Yeah. So my name is Ryan Falkenstein-Smith. I am a mechanical engineer at NIST in the Fire Research Division. And I am the project lead on the Smart Firefighting project, which focuses on developing different technologies that help mitigate risks for firefighters in the field. And one of the things that we started looking at was, hey, is there a way that we can start investigating things post-fire? And that mainly a lot deals with soot deposition, which we're going to talk about today.
Very cool. And the same for you, Amy. Can you tell us what got you involved with this project?
Sure. Yeah. My name is Amy Mensch. I am a mechanical engineer as well in the Fire Research Division at NIST. I am the project leader of a project called Building Fire Safety Evaluation. And that project basically is looking at engineering solutions for fire safety. The easiest one and simplest to understand is smoke alarms and smoke detectors. So we do a lot with it, different technologies, and also understanding how they improve fire safety, quantifying that improvement. So I became interested in engineering and solving problems, at an early age. And after I graduated and got my degrees, I was interested in solving the problems in fire research too, specifically because it's so multidisciplinary. And, we are both mechanical engineers, but we work with chemists, physicists, and also deal with practical engineering constraints all the time. It's also very relatable discipline because we're working on problems that people recognize and understand, like smoke alarms. And fire is something most people have some sort of experience with. So when I talk to family or friends, they can pretty easily understand, the big picture of why I'm doing whatever research problem I'm looking at. So yeah. It's been really rewarding to work in this area.
Now, what exactly is the Fire Research Division at NIST? And I'll ask that question to either one of you.
Yeah, it's a great question. The Fire Research Division is celebrating its 50th anniversary. In 1973, there was a report put out called America Burning, which highlighted a lot of the challenges that were being faced as a country dealing with fire. A lot of things that were being developed in terms of forensic analysis and arson investigations didn't have really established techniques that people could kind of hang their hat on and start looking into how can we actually use fire science to determine things like where was the fire, how did it happen, what ignited, things like that are very important to understanding why things burned down. So in 1974, the Congress put together the Federal Fire Prevention and Control Act, which founded the Center for Fire Research, which is now known as the Fire Research Division at NIST. And we've basically, as Amy said, participate in a lot of different activities from fundamental fire science research, looking at why things burn, how big fires are, different scenarios that cause ignition as well as affect different emissions and looking at environmental impact. And then also take that research and inform codes and standards by working with organizations such as ASTM or the National Fire Protection Agency.
So let's dive a little bit into some of the fundamental science that you do. Can you explain how the photoacoustic effect works in your study and why it's well suited for measuring soot deposit?
Yeah, I think to understand what we're talking about with soot deposition, we have to kind of go back to what motivated this work. So a lot of times as a scientist, you're dealing with more routine things on a daily basis. And sometimes, especially on a Friday, it's nice to mix things up. So we were doing these experiments in a very small compartment where there was a lot of soot that was deposited on it. And play around, somebody had a light similar to what a camera would have, and they put it very close to a wall that had a lot of soot. Well, if they projected that light onto the soot, it made this really cool popping. So we spent the rest of the Friday looking at the soot and the same light intensity and then characterizing the popping noise, in other words, measuring the acoustic or the sound, and then showing that the sound wave corresponded to the amount of soot that was deposited on the surface. And that's kind of interesting because, as I said, deposition and how soot is deposited on surfaces plays a role in determining fire forensics and understanding how a fire scenario happened in an applied world. So when we talk about the fundamentals of this, essentially what's happening is you have a light source that's very, very bright for a very short amount of time that emits energy in the form of photons, and those photons interact with soot. The reason why they interact with soot is because soot has these absorption properties or absorptivity in which they can hold on to the photons, take that energy and get very excited, and then have to dissipate that heat and energy very, very quickly, causing a popping noise. So what we're doing here and what we're talking about is characterizing the quantification of the soot noise to the amount that's been deposited. Is the intensity of the sound or how loud the sound is corresponding to how much soot is on a wall? And that's kind of the fundamentals of soot deposition via a photoacoustic technique.
That is actually fascinating. So just to make sure I'm getting this correct, it sounds like this research began by accident, just by somebody taking pictures or shining the light. Is that what I heard?
Yeah, I mean, some of the things that have just, hey, this is a very interesting technique, and can it be applied to certain things? I think as scientists, we ask questions about why is this happening and want to expand upon that and understand it. As engineers, want to take that science and apply it in a certain way. Amy said, given that our division is cross-disciplinary of mathematicians and fire scientists and engineers, we really have a blend of here's a fundamental problem and here's how it can be applied.
Before your research, what were the common techniques for measuring soot deposition and what limitations did they present? I may ask Amy this?
Yeah, sure. So a lot of the work that I had been doing previously was in measuring soot because I'm looking at other problems related to smoke, and soot deposition is something that we are interested in measuring for a variety of reasons. When I first started at NIST after my PhD, we were interested in seeing if we could measure soot deposition with a interdigitated comb that after the soot coats the surface of the interdigitated electrodes, it actually bridges the gaps and is conductive. And you can measure the change in the resistance of the circuit. This was something that, maybe interested in looking at measuring soot deposition after a fire in a cabinet to see how it affects electronics and damages them. So that's one method. The most simple method is just in research anyway, is to weigh a target, put it on a surface, and then weigh the change in mass. So you obviously have to have a very sensitive balance to get the right, to get an accurate measurement, but it's very accurate as long as you have that location defined and the area. Both of those techniques involve some kind of modification of the substrate you're looking at. So in a real fire scenario, when you want to measure the amount of soot that has been deposited on a surface, you didn't pre-weigh anything or do anything to the surface ahead of time. You're limited to maybe taking pictures and looking at the grayscale, or there isn't much else you can do. Taking a sample and trying to quantify the amount of soot by wiping it off in some way. So those techniques have challenges to them. The grayscale imaging, you might have issues with lighting, and also because soot is so black, increases the darkness level up to a certain point. But then at some point you add more soot, and maybe the just as black. There's no more change in the color. So this technique that we were looking at, we were hoping would, be able to deal with some of those challenges because it's related to each particle of soot interacting with the light. So it should keep going up as the mass goes up, even though you have more soot deposited.
So when you're looking at some of your designs with photoacoustic experiments, your experiments use camera flashes that generate a photoacoustic response in soot. Now, what made this choice of light source particularly effective?
Yeah, so that's a good question. When we were working on this project, we wanted to get something. The first iteration Ryan explained was a camera flash that they had lying around. Worked particularly well. It generated a sound that they could hear. So we started there. We started looking around to see what commercial camera flashes were on the market, and found one photography is pretty advanced. So we were pretty confident that it would be a pretty robust and repeatable source. Also, cost was a factor. We wanted to get something started and get it going. We could have looked around and got $100,000 light sources, but we wanted to get something manageable. So it turned out that, that worked out well because we had demonstrated it before and it was good enough. We could also, the light source that we ended up getting, we could control a little bit more. We could modify the intensity between a few different settings.
You calibrate the system to ensure the accurate sound pressure ratings from the microphone. And what challenges did you face when isolating a signal from background noise or interference from a flash?
Yeah, sure. So there are microphones that you can buy that are very, very sensitive. And with those sensitive microphones comes a particular noisemaker. I forget the exact name that you have, but they essentially have a controlled audio signal at a certain frequency. And what you can do is you can calibrate the microphone that you have and the signal that it outputs into some way it's being recorded. So when we're calibrating the very sensitive microphone, we're basically just controlling the sound level using this special device to calibrate that and then just record the sound level that we're recording on like a data acquisition system. The problem that you have in certain cases is you have a lot of background noise. As podcasters, you're probably very well aware of background noise.
Absolutely.
So we kind of wanted to isolate that by putting in a kind of small anechoic chamber or a soundproof chamber that somebody might have with 4 walls that kind of just controls the amount of sound that's coming from outside of where you're trying to sample from. Very sensitive microphone, and then also just kind of mitigating the background noise as much as possible. But surprising enough, when we talk about the sound that we're referring to here, you can audibly hear it, similar to how I'm speaking right now, or if I clap my hands. It's not something as soft that you have to be very, very quiet in a room. So, you can, audibly hear the intensity of the noise, which kind of prompted this whole thing of, hey, we're actually hearing a difference. As scientists, we're just doing our due diligence by actually measuring and quantifying it, is what NIST does best.
There was one other challenge that we had to overcome was that the flash itself makes a clicking noise when it's activated. So, even with, we did testing with boards or substrates that had no soot on them. So even with a clean substrate, we are recording a sound pressure difference. What we ended up doing was looking at the difference between, the sound pressure that we measured with soot and then the sound pressure, subtracting the sound pressure that we get without soot.
A key finding of your research was that the photoacoustic responses were consistent across different substrates, that is, say, drywall and metal. Can you explain why the substrate material didn't significantly impact the results?
Yeah, it's rooted in the absorptivity of soot. So if you think about how light is basically reflected or absorbed by different substrates and how it interacts, those photons that are projected from light sources interact with the medium in which the light is hitting. So in soot's case, because of its absorptivity, it's basically absorbing the photons as energy and then having, again, to dissipate that energy very quickly, which creates the audio noise. If you have something like gypsum board or metal or cement or wood, light doesn't interact the same way. It doesn't have the photons in which the particles that are sitting on that substrate get very excited and cause some audible noise. So what we're seeing here really is the direct interaction between soot particulates that are deposited on a substrate and the light itself. We're not really seeing any interaction between the light source and the acoustic noise. And some of the papers that we put out on this subject, you can see that if we do metal or if we do gypsum board or if we do repeats, it all is kind of falling on the same curve in the sense that it's independent of the substrate of which soot is deposited on.
Do you anticipate that the substrate independence would extend to other materials like glass and wood and concrete in real fire scenes? And how important is the versatility in practical applications?
Yeah, if you think about a fire scene that a fire investigator might arrive to, right, and we go into a house, it's not directly drywall, it's not just metal. It could be furniture, it could be made of wood, it could be glass on the windows. So having an application that it's independent of the material of the substrate and that you can apply it to different things is critical for its use. So, if we theoretically think about the interaction between the light source itself and the soot that's deposited, again, it's really just that interaction. It's not the substrate of which the. So if I'm a fire investigator and I arrive on the scene, I'm really just focusing on the soot deposited on different substrates. And it could be across something like a wall and then a window and then a wall again, in which I can just hit it with these different consistent light sources and get an acoustic response that's going to just tell me the soot deposited on the wall, because that's the only thing the light is interacting with. Now, I'll preface this as a scientist that we haven't investigated all these materials such as glass and wood. But again, looking at the research that we have and the various substrates of metal versus drywall. That being said, too, we also investigated drywall with different paint on it. And we saw the same thing when you have a consistent light source. The interaction of soot and the photons projected from the light source falls on the same curve, meaning it's consistent and, again, independent of the substrate.
Can you also tell us a little bit more about the intensity of light flash and some of the acoustic response that you get when doing these experiments? So I noticed when reading some of your papers that you do have 2 different flash intensities in your tests. How does the varying intensities of the light affect the acoustic response, and what trade-offs exist between higher and lower intensities?
Yeah, so that's a good question. As we were building this device, it was sort of a prototype, and we wanted to investigate varying different parameters. So that was important that we were able to vary the flash intensity just to be able to see how the response was affected. And what we found was really interesting, that lower flash intensity, maybe as you might expect, gave a lower response. And, we varied the amount of soot that we exposed the flash to. So the difference between them wasn't always the same. So, the curves intersected and, pretty much gave almost the same response at a lower amount of soot on the wall. But as the amount of soot increased, the difference, flash intensity, made much more of a difference. So it just comes down to basically whatever ends up being, like, if this is a product that is used by fire investigators, whatever flash intensity that they're using has to be that there has to be some sort of calibration that ties that back to the amount of soot that you were going to measure. Additionally, the distance from the wall also is going to have an effect. The sound is going to dissipate, and it's going to reduce the farther away the microphone and the flash are. Have a chance to vary that yet, but we anticipate that is less of a factor as opposed to, the difference in a major difference in the flash intensity.
So have you found a threshold where it's essentially too weak to detect yet, or are you still looking for that?
So we haven't fully explored the bounds of this device yet. From the graph that we're getting, it looks like we get a good measurement range within soot deposition amounts that you might see. So we're just basing that off of the look of the wall and, how fire scenes look. And so it's in a similar range that, this is applicable to a real fire scene. So that's important. And we didn't actually go any farther. Like, all of the range that we tested, it was giving a good response. So we weren't able to, find that yet.
Yeah, I think one thing to keep in mind when we're talking about the limits of detection is how sensitive of a measurement do we need? A lot of times when we talk about NIST and we're talking about very, very accurate measurement science, that has a high dollar value to it. Whereas in the field for a fire investigator, they're looking for something not only that gives an immediate response, but also something that's cost effective and fairly low cost. Having something like a camera light that's very accessible and doesn't have to be a very sophisticated instrument is pretty advantageous. So when we talk about, very low amount of soot, well, how good is good enough? Because at the cases that we were running, visually you can barely see the soot deposited on the lower end, but we're still seeing a very strong acoustic response. Now, it's possible that we can get a better acoustic response But in that case, is it really going to tell us something?
That actually relates right to fire forensics and safety research. In forensic fire investigations, burn patterns are often subjectively interpreted. How could your photoacoustic soot measurement technique bring more objectivity and precision to analyzing burn patterns?
Yeah, one of the things that Amy mentioned before is an easy tool that fire investigators have when they arrive on a scene is a camera. Right? We all have cameras on our phone. Cameras are very accessible. So you might take a lot of images of things. But the problem becomes more or less when you get to these darker concentrations, so there's high amounts of positive soot. In years past, when fire investigators arrived to a scene, a common practice was where the wall is white in terms of it looks like there's not a lot of soot deposit on it. It usually indicates where the hot zone was. In some cases, you think about a white spot with, soot deposited on the walls, basically pointing. People used to indicate that that is where the origin of the fire was. What we're here from this technique is providing a better resolution that quantifies the amount of soot. Now, when we talk about fire origin, you can think about soot deposited in certain areas and the spread of that origin of the fire and how it spread across the wall and substrates. And the amount of soot that's deposited on that can be indicative to how the flames spread throughout a fire scene. By quantifying that measurement, you're getting a better idea of the flammability, the spread of that flame as it moves through the room, as opposed to just taking an image and then kind of guesstimating what happens. And that's not to say people are guesstimating. You can apply other techniques that we've talked about, like just using a grayscale and quantifying it. But you're going to run into limitations of that. Here, with the technique, we're not running into those limitations based on the soot deposited. And that means it's really telling a lot of fire investigators different things like how soot deposited, where exactly was the fire, other information that is more concrete because you have a quantitative measurement.
Could this technique be deployed directly at fire scenes, or would investigators need to collect samples for lab-based analyses? And how portable could the system become in the future?
I mean, our idea more or less is, we're using bulky, a little bit more sophisticated equipment, but imagine a handheld device that somebody could just arrive to a scene and just perturb with light at different locations and get an acoustic response using somewhat of a sensitive microphone that can pick this up. Amy, do you have anything you want to mention on that?
Yeah, I think the answer is yes. That's what we're hoping for, is that it can be deployed, directly at the fire scene. It would be a tool for fire investigators to use, and that they wouldn't need to keep track of samples. It would definitely require, photography as well to understand the scene. But, this could hopefully quantify the soot deposition better for them.
Yeah, and to put it in a perspective that you might understand, imagine if you are my boss and you tell me, hey, I want to know how much soot was deposited here. Well, what you would need to do is a very invasive process such that you're digging into the wall, very carefully, mind you, to make sure that you're not actually getting the soot off the sample that you're trying to measure. And then you would have to send that to a lab to get an idea of the soot deposition. Whereas here, it's non-invasive. You don't get your hands dirty in a more metaphorical sense, but you're getting a more answer that's quantitative, that is not disruptive to the scene at all, which is pretty powerful.
Absolutely. Now, out of curiosity, beyond fire forensics, are there any other fire-related problems that could benefit from this? So whether it's insight into the intensity and the duration of the fire exposure, and even in a research setting?
Yeah, so that's actually a really good question. We have been thinking about that too. I mean, we doing fire research experiments in our lab. We think this tool has great potential for us too, and the questions we're trying to answer, which are, those types of questions. What was the heat release rate? Like, can it, give us more information about the larger problem? I'll say that this kind of tying it all together is the effort to do fire modeling. So this effort is a comprehensive fire simulation that, models the computational fluid dynamics, the heat transfer, the combustion, the smoke and soot deposition. NIST has developed a model, and we maintain it, called the Fire Dynamics Simulator. And this code is used by thousands of fire protection engineers worldwide. So, we're always trying to improve that model. And this measurement tool is something that we're really excited about using to be able to validate our soot deposition models in particular, and also just understand different fire scenarios that would create different burn patterns and really improving the science-based understanding of fire forensic investigations.
In the context of life safety predictions, soot deposition means soot has been removed from the air, which affects visibility and smoke toxicity. Could this technique improve how we model or predict factors during fires?
As Amy mentioned, one of the greatest things that have come out of the fire research division at NIST has been the fire dynamics simulator. And a component to that is something called smoke view, which essentially provides an idea of the visibility within a room structure. And if a fire is happening and you're generating smoke in there, you can get an idea of the opaqueness or the transparency such that somebody can visualize an exit. One thing that I think the model's being challenged on, and especially where our tool can be helpful, is the amount of soot deposited onto certain substrates and get an idea of how something can be compromised post-fire event. So predicting certain things of the soot deposition can kind of be very informative to, how fire started and other things that forensic investigators might look at. When we talk about FDS, it's used worldwide by a lot of fire protection engineers as well as fire investigators. And validating that model via this technique that we developed is very, very critical. Another step that we've been talking about that might be useful in the future that extends a little bit beyond what we're doing now is potentially using AI to get an idea of recognizing position patterns that is informative to fire sources and fire spread in different events. And through the efforts of a FDS model that basically gives you an idea of the deposition, as well as this technique that quantifies the amount of soot, that would be very informative data to building an AI model that improves prediction.
A fire scene, when a fire investigator arrives, it can be pretty chaotic, although they aren't really allowed on scene until the suppression activities are complete, no more fire or smoldering is occurring, and the fire service has deemed it safe for entry. So that being said, it's definitely not a controlled environment. There's a lot of range in possible temperatures, whatever is experienced outside, or humidity. So yeah, the different elements, could affect the measurement. And at this point, we don't know exactly what the effect would be, since we only conducted the experiments in the lab environment. Although we have tested it out in a compartment that had soot exposed to it that was in a lab that wasn't controlled. It was basically humid and hot as the outside air, and pretty much got the same response. So my guess is that it wouldn't have too much of an effect, and not significant enough to be outside of our error bars.
There any improvements and advances that you are going to want to make in the near future, whether that's more sensitive microphones or more powerful flashes?
Yeah, I one of the things, if you read our papers, that you'll notice is the camera flash that we were using is fairly big and bulky. And if you take that and you take the data that you're getting from that, in other words, how much of an area on the surface is actually being hit with light and then getting a photoacoustic response back, it's fairly big. The difference between taking an image is you can take those tiny pixels and you can assign some grayscale value to it and get an idea of soot deposition. So the resolution is much, much better. So one thing that we're talking about with the improvement is scaling down the area of which light hits the substrate with soot on it, such that you're getting more of a smaller local region, such that the soot gets excited and you can characterize on a little bit more of a finer scale. Now, when we talk about different applications, it's possible to use a little bit of a different light source that acts in the same way, such that it's delivering photons to soot particulates and exciting them to get an acoustic response. And one of the things that you're talking about is, looking at something like environmental sampling. So imagine if you have a continuous gas stream that has particulate matter in it, that you're exciting those soot particulates in the gas stream. But you're also measuring gas concentrations using paramagnetic sensors or NDIR sensors. You can also use something like a TIC or a thermal imaging camera to get an idea of the temperature distribution as well as the concentration of the soot within that environment. So kind of that's where we're interfacing some of the other technologies that are there. But the bigger thing is improving the existing technology that we have, such that we're getting more of a refined, resolved measurement that's competitive to other techniques that are out there.
I'd love to talk about some of the broader applications of the photoacoustic technique, for example, in industrial environmental monitoring. Beyond fire scenes, could this photoacoustic technique be used to monitor particulate pollution in industrial settings or, say, emissions from combustion processes? How adaptable is it for environmental monitoring?
The answer is possibly. This photoacoustic technique really needs a high signal to noise to work. So as far as we understand, there have been challenges to implement it to measure soot in the air, like aerosolized soot. We did find in our literature review, we did find a patent from 20 years ago to measure particle concentration using a pulsed laser. But, I've been in this field for a decade or so, and I have not heard of it being used to measure particle concentration. So that's my take, is that it really probably is difficult to implement, as opposed to, our implementation of a surface measurement and, very close light and microphone source. We're kind of optimizing the signal to noise in that case. So, that being said, I could talk a little bit about what kinds of technologies are typically used for concentration monitoring, which we are working on too. We use light extinction measurements to typically measure smoke concentration in large ductwork, because we have, when we do large fire experiments, we have, large hood above where we are capturing all of the exhaust. And, you can shine a laser through that ductwork and basically measure the obscuration of the light. What signal you have coming in, you measure the change in the signal as it's being attenuated through the smoke. And, through a long path length of a ductwork, that's a pretty accurate measurement that you can tie back to your concentration. As far as environmental monitoring, the sort of gold standard is slightly different because you have usually a smaller sensor. So you can't have a large path length of the laser. So in that case, typically what is used is light scattering. This is also the technology that's used in photoelectric smoke alarms. So in that case, you have a light source laser coming in to a small sensing volume, and then you have an off-axis detector, which is measuring, it's very sensitive, and it's measuring the small amounts of light that are incoming that are also scattered from the particle. And that's, like I said, used in photoelectric smoke alarms. It's used in low-cost particulate matter sensors that, marketed to give you the PM 2.5 that is in your environment. And, that's becoming much, much more important now, when you may be exposed to a wildfire smoke, even from Canada or, in your local area. These smokes are traveling very far and affecting air quality. So that's something that we have been looking at too. How does soot as an aerosol respond to that light is actually different than other types of aerosol particles, because soot has this long fractal-like structure. It's not a sphere, which typically is assumed for light scattering. And so it doesn't scatter light as well, basically, compared to spherical particles. So often these low-cost particulate matter sensors, low-cost PM sensors, are underreporting soot concentration compared to other spherical particles like small droplets, liquid droplets, for example.
But just jumping off of that too, soot is a very retentive to certain components such as polycyclic aromatic hydrocarbons or PAHs, or other components like PFAS or polyfluoroalkyl substances. Because of its carbonaceous nature, it wants to just retain these things. So when we talk about environmental modeling, or monitoring, excuse me. And we're talking about getting the idea of soot deposition. Imagine there's a wildfire that's in another state or in another country, and you see the atmospheric winds just kind of bring it in, and that smoke penetrates your house. You might see deposition, or if your house survives in a wildfire and there's maybe some funky smell that might be on the wall. Well, not only do you have this photoacoustic technique that maybe can measure at very low concentrations how much is on there, but there's also possibilities in developing correlations to, well, the amount of soot that's deposited on there could be linked to certain components that are retentive to soot. It's not necessarily a direct way of environmental monitoring, but it might be a new way of what we can look at, as smoke penetrates our house, is the clean? What exactly is on that soot that we might want to be concerned about?
Now, could the technique be useful in historical preservation or archaeology, where understanding the deposition of materials on surfaces is critical? I know you talked about stuff with burning buildings and soot deposition, but how does that play in on a historical context?
Yeah, that is a fantastic question. I mean, I just want to make it clear that when we talk about this technique, it's mainly in the context of soot, because of soot's absorptivity, its absorption properties, and the interaction between light and soot. We talk about things like dust and ash and all those other components. There's little interaction that might be going on between a light source and soot, or a light source and ash and those other components that aren't necessarily soot. But talking about it from historical artifacts and preservation, fires do occur. And a big concern in certain cases is if there's a fire in a museum or in an archive location where we have very, very important documents that need to be preserved, there's cleaning processes associated with that. And one thing that we've had experience with is the Smithsonian has come and done experiments where they will build a structure like a room, and then they'll burn with some artifacts, kind of not necessarily artifacts that are very important, but kind of substitutes. And what they'll do is they'll work through cleaning processes based on the fire scene and how to clean things appropriately. Imagine if you had a technique like we do here with a photoacoustic that you can actually measure the deposition. So that might not be important in sense of I'm cleaning off the soot and I don't see it anymore, but it might be important to actually measuring how effective the cleaning process is. So if you have soot deposited on something and you want to make sure that it's pristine such that there's not residuals on there that could cause the artifact to degrade even more, this is a way to kind of measure that. And so you're kind of improving the preservation of these artifacts if a fire does occur. So it's another way to kind of confirm the effectiveness of how something's being cleaned.
One of the things I wanted to ask you guys is about working with fire for as long as you've been working in that area. What are some of the coolest things you've gotten to witness or learn along your journey?
Yeah, so when I first started out in fire research at NIST, I was in the firefighting technology group, and I was doing research on the thermal performance of firefighter respirators. So the face pieces that they wear to, protect their breathing, there was, some concern that they were actually melting and degrading with thermal exposure because they were made of plastic. So that was really interesting work. I got to interact with firefighters on the committees that developed the standard for that equipment. And also the really interesting, more exciting part of that work was I got to travel to Chicago where they were about to demolish some townhouse, area of townhouses next to the O'Hare Airport. And we had some basically burns in those townhouses where we had the Chicago Fire Department there to put them out. So I got to see them put out a fire. I got to experience it. And, we took all kinds of measurements. We exposed some firefighter face pieces to the fire. It's a really, really interesting and fascinating experience.
What about you, Ryan?
One of the things that I love about working in the fire research division at NIST is that because we're interdisciplinary, such that we invite, researchers with mathematicians and physicists and chemists, there's always something new to learn, and there's always a lot of fun projects that you're looking at things from different perspectives. One thing that I got to work on, and I'm actually kind of still working on this, is we investigated the development of backdraft in terms of backdraft in the sense that you have a very isolated compartment that's hot and fuel rich and doesn't have a lot of oxygen. In a fire scenario, you open a door to this environment, and what happens is air rushes in, it mixes with that unburned fuel, and then it ignites, causing a deflagration or a fireball basically to eject from the door, which basically the air came into. And for firefighters, that's a very scary thing because they don't necessarily know when they approach a door if a backdraft's going to occur. And there's not a lot of measurement techniques right now that can kind of quantify a backdraft event. One of the things that we started working on in 2020 was, can we actually develop a technique where we can predict the likelihood of backdraft using common measurement techniques? So what we did is we built this reduced scale enclosure. It's kind of like a meter by a meter by a meter and a half. And we just filled it with fuel inside this compartment and had a very limited oxygen environment. And we basically had this robot control door in which it would ignite and cause a backdraft, or it wouldn't ignite. And we had over 600 experiments in which we have all these different conditions of measurement, such as temperature, such as pressure, and ventilation, or the equivalence ratio. Equivalence ratio in this sense, I mean of how much fuel to air there is. And we take all those different parameters and we were actually able to integrate it into a logistic regression model such that we can now measure the scenario that we have, the likelihood of backdraft of different scenarios of which, hey, it's a 50% chance or a 60% chance, which is pretty exciting because it uses a little bit of AI to input all those parameters and then output a likelihood such that you might have a way to predict the likelihood of backdraft using this tool or using this technique. That's been very exciting. We've also looked at some mitigation tactics of that environment and how to reduce the likelihood of backdraft, either through ventilation or through suppression. But that's been a very exciting thing, and I'd be more than happy to kind of share some work on that and some videos that we have, because backdraft, describing it, but a picture's worth 1,000 words, and it's been very exciting. But there's been other things that our research division does is large scale environments. One thing that we recently did is we burned cars, not EVs, but just ICE and cars, IC engines, internal combustion engines. And that's been actually pretty interesting. The work isn't out there yet. It hasn't been published, but one thing that we're looking at is kind of get an idea of the fire size when you incorporate different components in there, as well as the emissions, not only soot, but also things like PAHs, PFAS, VOCs, volatile organic compounds, SVOCs. And we have the capability of looking at that because, again, we have people from various disciplines. It's very exciting work, and I'm always excited to come to work to see kind of not only what we're doing, but what we're burning next.
I do have one final question for the both of you. Out of curiosity, are there any important takeaways that you want people to know about fire science, whether it's your research? I'm leaving this as like a very broad and open question.
Yeah, I mean, fire touches a lot of different areas of the world, and I can't imagine any one particular field that isn't affected by fire. And that means essentially it's inviting various disciplines to kind of apply different perspectives on things to reduce risks associated with that, either through direct thermal exposure or from the environmental exposure that we might have from these things. One of the exciting things that we really kind of get to do here at NIST is develop tools and implementing them to kind of solve certain problems that improve people's way of investigating things or measuring things. And it's exciting to kind of see where we're going over the next 10 years in terms of the fire research division and how we're going to expand not only a photoacoustic technique, but also kind of other areas that we're looking into.
Wonderful. Amy, what about you?
Yeah, I think one thing Ryan mentioned is developing measurement tools. And, that's a huge part of what we're doing. We're not necessarily always seeing what we do in application, but, we're trying to get our knowledge out there and see how the market uses it, see how, standards committees use it and practitioners. And it's always rewarding to see it get picked up. This has been really interesting how this particular application has been, seen a lot of interest. And, it is a very cool phenomenon. Most people don't believe that the soot can actually make a sound until we demonstrate it for them. So it's, been a really interesting way to get people's attention to all of the other problems that we're trying to
too.
Absolutely. Now, is there anything else that you would like to add in before we wrap up the session, or anything that we didn't cover?
I'm good for now.
I think we kind of touched on almost everything.
Yeah. No,
Okay.
This has been a pleasure. Thank you so much for having us on.
And thank you both for coming on Breaking Math Podcast. And